the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for pre-calculus students and linear algebra students who are currently going through matrix methods, and that would be matrix algebra and inverses of matrices to solve large linear systems, that type of thing. Our goal in this video is to talk about a brand new method, at least somewhat new to you guys. You may have never seen it before, then therefore it is totally new. But it's not new to the game of mathematics. The method is called Cramers Rule. It will allow us to solve a system using determinants as long as that system's not too large. One thing to note here is that Cramers Rule is actually a pretty inefficient method. So when you learn Cramers Rule, and I remember learning this when I was a student and thinking, wow, this is a pretty easy rule to use to solve a system or to solve a matrix equation. The problem is that Cramers Rule relies heavily upon computing determinants, and the computation of a determinant can be laborious at best, especially when you get to large matrices. And so the computational cost of using Cramers Rule is pretty high. However, there is a lot of theory that's kind of important from Cramers Rule that we're going to need. So let's go ahead and learn Cramers Rule. Cramer's rule goes like this. Consider the matrix equation AX equals B. And we must, by the way, assume that A is invertible. I don't think I said it in the previous page, but it is true. A has to be invertible. So consider that matrix equation where A is an invertible n by n matrix. What we're going to do is build a brand new matrix. And that brand new matrix we'll call A sub I of B. Now there's a lot of different notations for this matrix. When I learned it, it was called D sub X and D sub Y and D sub Z, and it still might be called that in the textbook that you use. However, in the textbook that I use, it's called A sub I of B. It's a function actually of B because what you're doing is you're plugging in a vector B, specifically the vector B in the matrix equation right here. You're plugging that in and replacing the ith column of A with that vector B. So A sub 2 of B would take your matrix A and replace column 2 with the vector B. A sub 3 of B would replace column 3 with B, and so on and so forth. And you might think to yourself, okay, that's weird. Why would you do that? Well, we're going to go ahead and, like I said, let A sub I of B be the matrix obtained from A by replacing column I with the vector B. The unique solution of the matrix equation, and remember, because A is invertible, that matrix equation totally has a unique solution. Anyway, the unique solution of the matrix equation has entries given by the following. And you would do that for every entry in the vector X. So if you have 10 entries, you would have 10 of these computations. It's actually 11 determinants because you have to initially take the determinant of A, and then you have 10 of these determinants right here, and then their divisions. For small systems, this is actually an okay method, but still, it's not super fast in any case. And as I mentioned down here, using Cramer's rule for solutions to systems might seem attractive. However, this method is computationally inefficient for systems of more than 2 or 3 equations. So let's see this in action. Solve the following system using Cramer's rule. First of all, I'm just going to write down, not that you would have to write it this way, but I'm going to write down the matrix A and the vector B. You always start Cramer's rule by computing the determinant of A because you're going to need that in every single one of your computations for your solution. I mentioned it in the determinant video, but I'll repeat it here that there is a method to compute the determinant of a 3x3 using a very special trick. However, I do not use nor do I teach that trick because it only works for 3x3s. Go beyond a 3x3 and it falls apart. So I'm not going to bother with it here, but I am going to expand my determinant about column 2 here. So let me go ahead and just write in the coefficients of the cofactors. That's the signs of the cofactors. So plus, minus, right? That gives us the pattern to how we're going to expand this. And I want to use our official notation for the determinant because it's going to be useful in another couple pages here. So the determinant of A, if I expand about the second column, will be the following, where A12, A22, and A32 are just these entries 2, 0, and -4, and C sub 12, C sub 22, and C sub 32 are the cofactors for our matrix A. It's the 1-2 cofactor, the 2-2 cofactor, and the 3-2 cofactor. If you don't remember cofactors, please go back to my video on determinants because that's going to be a big conversation in a few moments. But essentially, a cofactor is just the plus or minus sign that you see up here times the minor of that entry. So for example, the minor of the entry 1-2, which is this entry right here, A sub 1-2, is the determinant of the matrix had you removed that row and that column from this matrix here. Again, that conversation is going to be very important as we move forward. Let's go ahead and just compute this out. What I've written there are just the entries A12, A22, and A32. Now we'll write in the cofactors. So the A12 cofactor is the sign that you see here, the negative, times the determinant of the matrix that remains after you remove the column and the row that you're currently looking at. Luckily, our next term is plus 0 times who cares, because 0 times anything, well, that's just 0. Finally, we have this entry -4 times the cofactor of A sub 32, and the cofactor of A sub 32 is going to be that red negative times the determinant of what's left over after you remove row 3, column 2. Now, obviously, you shouldn't take that long to do this style of computation, but you get faster with time. So let's go ahead and compute this out. So I get that the determinant of A is equal to 10. Now to use Cramer's rule, you'll have to do 3 more determinants because this is a 3 by 3 matrix. Each determinant of a matrix where a column has been replaced by the vector B. So let's go ahead and do those here. So this notation means I'm going to replace column 1 with the vector B. And you could see, very similar looking matrix to what we have originally. I'm still going to expand about the second column. This time when I expand about that column, I'm just going to immediately dive into the expansion without worrying about labeling things. Barring any copying or arithmetic mistakes, let's go ahead and continue forward. All right, so that determinant is -10. Let's go ahead and do the next one, replacing column 2 with B. And you begin to see an issue in that if your original matrix had, let's say, some zeros you could take advantage of, eventually those get kind of removed in one of the methods. I'll expand this about row 1. And continuing forward, this is going to be 5 if everything is correct. And finally, let's replace column 3 with B. If you notice I'm constantly zooming in and zooming out, it's because I'm checking my work, making sure I'm copying things correctly. I will go ahead and expand this about the second column. And computing this out, I get that. Now it's time to actually showcase how we get solutions using Cramer's rule. By Cramer's rule, x sub 1, remember our vector x has 3 entries, x sub 1 will be the determinant of a sub 1 b divided by the determinant of a. Let's see, determinant of a sub 1 b is a -10 and determinant of a is 10. Great, we have the first entry in our solution. Now we go for the second entry, a sub 2 of b is 5, and again, determinant of a is 10. And finally, let's take a look at a sub 3 of b, that's 30, divide that by 10, and we get that, 3. So our solution vector is supposedly -1, 1/2, 3. Let's go ahead and check that against this system here. Imagine plugging in a -1, and then a 1/2, and then a 3. That would be a -1 plus 1, those cancel, and then -3. That works for the first equation. Trying it on the second equation, we get a -2 plus 3, that's definitely the positive one, so that works out. And trying it against the third equation. Negative 3 minus 2 more is negative 5, plus 6, that is a positive 1. All of these work out beautifully, so therefore that is definitely the solution. It checks out. Now you may wonder, how the heck does that check out? Like, how does that even work? Well, to be very honest with you, there are actually quite a few proofs for Cramer's rule. However, the best one I've seen is actually from the textbook I use. So if you're able to get your hands on the lay textbook, it's a really well done proof, but I'll try to mimic it best here. We're going to start with the assumption that A is invertible and that A is the matrix A sub 1, A sub 2, all the way over to A sub n. Now we're going to do something kind of weird here. We're going to take the matrix A and we're going to multiply it by the identity matrix, but actually not the identity matrix. We're going to replace column I in the identity matrix with the vector X. Now remember, the identity matrix is a matrix with column vectors E1, E2, and so on and so forth. But then there's a column in here, the ith column, that we're going to replace with X. However, we know from matrix multiplication that this product will be written as that matrix right there. Those are all column vectors. A e sub 1 is a column vector, A e sub 2 is a column vector, and so on and so forth down the line. But one thing that we know is that we're solving ax equals b. So we know that a times x should be the vector b, which, if you recall, e sub 1 is the column vector 1, 0, 0, 0, 0, 0. E sub 2 is the column vector 0, 1, 0, 0, 0, and so on and so forth. So E1 times A is just going to return the first column of A. A times E sub 2 is just going to return the second column of A. And so on and so forth down the line. Remember, we have this ith column is going to be B. And then all the way down until we get to the nth column of A. So far, so good, hopefully. However, if you take a look at this by our definition, this is the same thing as saying, I'm going to take column I of A and replace that with B. So what have we shown? We've shown that A times the identity matrix where the ith column has been replaced with X is the same thing as A with the ith column replaced by B. However, the determinant of the product of these two matrices, and these are two matrices, this right here is a single matrix and this is a single matrix. We have a property of determinants that says the determinant of a product is the product of determinants. But remember, A times this matrix I sub I of X is the same thing as A sub I of B. So this determinant group here should be the same thing as the determinant of A sub I of the vector B. All these should be equal. If you divide this equation right here by the determinant of A, you get that right there. Now here's where the argument is very important. That identity matrix with the ith column replaced by X, it looks like this, where the ith column has been replaced with the vector X. Now imagine for a moment I wanted to take the determinant of this matrix. What you can actually do is expand this about that column that I've just highlighted. Now, I don't really care about the plus or minus signs here. I just want to showcase something very neat. So if I expand about that very ith column there, I'll have some plus or minus x sub 1 times the determinant of what's left over after you remove that column and that row. Well, pretend as though I removed that column. So you have just a bunch of zeros and ones that look to be upon down the main diagonal. But when you look at the resulting matrix, you get this, and this is actually upper triangular, believe it or not. And when you have a triangular matrix like this, well, the determinant being the product of the main diagonal, it's a bunch of zeros times that final one. So this is x sub 1 times a bunch of zeros. And you will find out, and I can't actually go through the whole thing because I have office hours that I'm late for, but you'll find out if you expand all these, the only one that remains with ones along the main diagonal is x sub I. So this determinant right here actually will become x sub I. And therefore x sub I is equal to the determinant of a sub I b over the determinant of a. And like I said, I apologize that I have to rush off, but I do have office hours I'm 5 minutes late for. So I hope you guys found at least the rule, Cramer's rule, and finding the solution easy to understand. And the proof is not so bad. Look in your text, you might actually have a very similar proof. Anyhow, I hope you have a great day. Be wonderful humans.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.